The last installment of today's lecture is to cover this sizeof operator. The sizeof is a built-in function in C++ that will return to you the size in bytes as an integer of whatever you specify here. So if I say, what is sizeof int? If I call sizeof int, C++ will return the number 4, although I say usually. In old school rules, an int could be a different number depending on your operating system. We don't use that anymore. So sizeof int should just be 4. It's nice to go ahead and use one of the new explicit types. Int 32_t, for example, says I want a 32-bit integer, and the underscore t just stands for type, I think. So int 32 type. And that will definitely return 4. It takes 4 bytes to hold a 32-bit integer. And then similar, there's a sizeof, you could do sizeof char. So that's going to be 1 byte. And sizeof bool returns 1 byte. Sizeof will give you the size of anything. And so if you declare this class test1 that has complex structure, has multiple things in it, has a char c and an int I, what is the size of test1? A char was 1 byte, an int is 4 bytes, a char plus an int is 8 bytes. Wait, what? Okay, if you said 5 bytes, that makes sense. I can see 5 bytes here. What I do not see is the alignment rule that this int is 4 bytes long, and therefore it has to be on a 4-byte address. The char is 1 byte long, so it can be on any address, but the int must be on a 4-byte alignment, so we can't have something that's 5 bytes long. 5 bytes long will not stack on a 4-byte boundary. We'll have to round it up to 8. So what you end up with is the C taking up 1 byte and then 3 bytes of wasted space, 3 bytes of padding before you get the 4-byte integer element. And this comes down to the assembly instructions that are available. So when you load from memory into a register, if you do one of those MOV instructions, and you load from memory into a register, if you load a byte, that'll go into one of those byte registers, and you can do that from any memory address. If you load an integer, that'll be into one of the integer registers, the 32-bit EAX registers, and the instructions for those can only load on a 4-byte boundary. If you load a float, that would be one of the either into the floating point registers or using more complex instructions into the SIMD registers is what we typically see now. Those have to be loaded from a 4-byte alignment. A float is 4 bytes, and the load instructions for a float are on 4-byte alignment. If we go to a SIMD, you want to load a whole SIMD, all 4 floats of a SIMD, it has to be, as we discussed before, on a 16-byte alignment. That's 16 bytes that you're loading with a single instruction, so it has to be on a 16-byte alignment. So that's the rule. That's what forces the rule, is that those instructions have that. So when you think of a more complicated structure, like this structure that has a byte and then a 4-byte element to it, the alignment rule for this structure, this class, is 4 bytes, because the largest thing in it that can be accessed with a single instruction of assembly is that 4-byte integer. So a test1 itself does not have 8-byte alignment. The test1 takes up 8 bytes, but the test1 itself is forced to be on a 4-byte alignment because the largest thing in it that can be accessed with a single line of assembly is the integer. Let's take a look at how this interacts in a more complicated scenario. For example, let's say we have a character, an integer, and another character. If we lay it out in memory, we will need the character and the 3 bytes, and then the 4 bytes, and then the next character. But because this entire class now has to have that 4-byte alignment to keep the I aligned, then we'll need padding at the end of the B as well. So now we have 6 bytes of padding. The compiler will not, the C++ compiler will not reorder the variables for us. However, we could reorder those variables to get this to pack more efficiently. So if we just put the two characters together, we now saved 4 bytes of that padding. We went from 6 bytes of padding down to 2 bytes of padding and made the overall structure smaller. C++ will not reorder the variables, and the reason for that is so that programmers such as ourselves can predict exactly how the memory is going to lay out with our structure. We can control how the memory is going to lay out with our structure. And the compiler won't be trying to override us. And the next thing you might ask is, well, if the B is the last thing, then how come I need these bytes here? And I would say, because I might want to make an array of these. If I make an array of test 3, the I of the next one needs to go down here on the 4-byte alignment. So it needs that 2 bytes of wasted space if I'm going to make the array. I mentioned before that we are using 64-bit pointers or 8-byte pointers. So if you say sizeof void star, you should get 8 as long as you're configured for x64. I don't think I've provided libraries for x86, so it wouldn't compile, but you could set your compiler to x86, which means 32-bit pointers. Like x64 for 64-bit pointers, that makes sense. You'd think x86 means 86-bit pointers? No, that just refers to the old Intel x86 instruction set. It's just legacy. That means 32-bit. And thankfully they changed it to a new system these days. Anyway, that sizeof void star, so size of any pointer, will be 4 if you're in 32-bit pointers, but we are in 8-byte or 64-bit pointers, so we will get 8 from there. And again, that will be 8-byte alignment as well. And yes, that does mean if you have a virtual in your class, you need 8-byte alignment for the class. So here's some useful types. I have shown the int32t before. Similarly, we have something called a size t. A size t is an unsigned integer that is either 32 bits long or 64 bits long, depending on which system you compile in. So for an older 32-bit system, you will get a 32-bit integer for that. For a newer 64-bit system, you'll get the 64 bits. There's another one that's the int_pitter t and the uint_pitter t, which is a signed integer or an unsigned integer of however many bits it takes to hold a pointer. So that's a very convenient way of just referring to if you need to do like just plain old school math, add a couple of bytes to your pointer, then turn your pointer into an int with an int_pitter t, and then you can just do regular math on it like it's any old integer. I had mentioned that typically a bool is a byte, but we know that a bool really only needs 1 bit. Turns out in C and C++, there's a way to tell the compiler to just use a single bit. So let's take this example. We have an integer and then we have a whole bunch of bools. And if we do size of that, we're going to get 12 because we got 4 here, 5, 6, 7, 8, 9, 10, 11, and it has to be a multiple of 4 because of the integer, so 1 pad, so we'll get 12. Okay, instead I use this colon thing. If I say A is a bool colon 1, I said I want a 1-bit bool for that. And I can then pack a bunch of other bits together into that same byte. So I have 1, 2, 3, 4, 5, 6, 7 bits used, and then I'll need one more bit to fill out the 8-byte bool, or I'm sorry, the 8-bit bool. And then that gives me 5, but I still need my padding, so that will be padded out to 8. So I did manage to take my 12-byte class and drop it down to an 8-byte class by using the bool bit trick. And by the way, you can say how many bits you want. It doesn't have to be 1. It could be, you could make a 3-bit bool, which is kind of silly. I don't know any reason to use a 3-bit bool, but you could make a 3-bit integer. That might make sense. If you had a very small range of numbers and you wanted to pack them in tight, you could do like 3 bits for that and 5 bits for this. That would be an 8 bits worth of integer value, and that might be something you might want to do. I also like to share at EA on Command & Conquer 3, they had a lot of bools in their class. The game object class itself, they had decided years ago not to use inheritance, and so every object was a game object. So absolutely every feature that anything could do was all crammed together into the class. So if anything could go stealth, then is stealthed is one of the bools on the object, and is vehicle, and every possible thing, is tree, is ship, it can fly. Every bool for any object at all was all crammed into bools within the class. And so one of the big optimizations that I did for them there was to use the bool bit trick to make that data size smaller, and then I also reorganized their bools into groups that would pack together efficiently, and as opposed to doing like bool int, bool float, bool int, which was an inefficient packing. So I took all the bools, put them together, and then made them all a single bit each to cram that down into a more reasonable size. This brings us to the quiz. Okay, it's not really a quiz. There's a video. So what's the size of this class? So let's take a look at this and see if we caught the little nuance that I mentioned earlier, putting this together with the virtual functions that we talked about. What is the size of this class? We have an integer here, and the integer is 4 bytes. We have a virtual function. So anytime we have the word virtual appears in our class, that means we have a virtual table. So that means every instance of this virtual class starts with a pointer. So there's a pointer and then the integer. And that pointer is going to be 8 bytes long, and it will need 8-byte alignment. So if we're doing 64-bit pointers, the pointer is 8 bytes, 8-byte alignment, and then we have the integer. So that means this is a 16-byte class. This class is 16 bytes long in order to hold that one integer. Bonus question. What if we reset the compiler to x86 mode and recompile? How big will it be then? Last but not least, let's look at, we've been looking at sizeof. Let's look now at a very similar operator called offset of. We can do offset of, which is very useful. I think some of us have already been using it. I suggested that we use it in the labs. I like to use it for my data structures a lot. Offset of tells you where in this structure does this element begin. So in this structure right here, where does I begin? And it's the first thing in there, so that should give us 0. And where is A? A comes right after I, so that starts at byte 4. So I'll give you byte 4. And then where is G? G is 4, 5, 6, 7, 8, 9, 10, and then comes G. So that should give you byte number 10. Some people ask, it's a good question, what if I had used the bool bit trick here and I had said that each of these is a one bit bool, What would then happen if I say offset of test4, comma G? I believe that that's a compiler error. It would say, no, I can't do that because offset of returns the byte offset, not the bit offset. And on that, let me make a note. When I give out assignments either on exams or in-class assignments and I ask you what is the size of something or what is the offset of something, I want the answer in bytes. I don't want you to tell me the answer in bits because that's not what size of or offset of means. Size of and offset of are built into the C++ language. They have a very specific meaning. They mean the number of bytes. And furthermore, I ask that you do not put 4 bytes. You simply say 4. The answer is 4. The main reason for that is that I've moved to GradeScope and I've set up auto grading for these things, and so it will not understand you if you put 4 bytes. It will only understand if you put the number 4.